Hello everyone, welcome to topic 6.3, heat transfer and thermal equilibrium. By the end of this, you should be able to explain the relationship between the transfer of thermal energy and molecular collisions. So looking back to 3.5 when we saw the Maxwell-Boltzmann distribution curves for substances at different temperatures, we saw that the Boltzmann distribution curve, we see that the particles with a higher temperature will have greater kinetic energy than those that are at a lower temperature. Please recall that temperature is a measure of the average kinetic energy of the particles of a sample and that the kinetic energy is equal to 1/2 mass times the velocity squared. So when hotter particles and colder particles are in contact with one another and they collide, energy is transferred between them. This is sometimes called heat transfer, heat exchange, or transfer of energy as heat. Like, they all mean the same thing. This results in the hotter particles losing some of the energy and colder substance increases in temperature or gains that energy. Heat is always transferred from the hotter substance to the colder one. There's no such thing as a cold transfer. It's always heat that is transferring. If the two substances result in the same temperature, we call that thermal equilibrium. When they result in the same temperature. When two substances reach the same temperature, they have the same average kinetic energy because they have the same temperature. Okay, so now we're going to apply some of these concepts and we're going to be reviewing some things too. So 50 grams of aluminum with a specific heat capacity of 0.9 joules per gram degree Celsius at 85 degrees Celsius is placed into 100 grams of water, which has a specific heat as follows. At 25 degrees Celsius, what happens to the temperature, average kinetic energy, and average speed of aluminum? Just as like a note, we will dive into this in a future section. This specific heat capacity is a measure of the amount of energy to raise the temp of 1 gram of the substance by 1 degree Celsius. So it's kind of a measure of how fast you can change that temperature. So a very low specific heat capacity means it needs very little energy to change temperature, so it'll change temperature faster, versus something with much higher specific heat capacity. So water has a specific heat capacity of 4.184 joules per gram degree Celsius. That means it needs a lot of energy before it starts to heat up. So when we look at these, what happens to the temperature, average kinetic energy, and average speeds of aluminum? So for this, the temperature of aluminum, if we're putting something very hot into something cold, we should see that the temperature decreases. That because our temperature is decreasing, that the average kinetic energy is also going to decrease because those are the same thing. And we should also see that the average speed also decreases. Alternatively, for water, they all increase so that they meet in the middle-ish for thermal equilibrium. Notice it's not a true average, but it's still based off of their specific heat capacities, their middle ground. Okay. So now looking at our WEDO, we have 50 grams of aluminum at 85 degrees Celsius is placed into 100 grams of water at 25. The final temperature of the two substances is 30 degrees Celsius. So that's the temperature for thermal equilibrium. What can be said about the temperature changes for each substance? that we would say that aluminum changed a lot more. And we could justify it as being due to a low specific heat capacity. And that water, if you wanted to go the opposite direction, increased much more. Okay? Or that the aluminum decreased and water increased in energy. What is true about the amount of thermal energy exchanged? The total amount, because it's thermal equilibrium and energy can't be lost or created, it has to be completely transferred. So the total amount is equal to what was lost by aluminum but gained by water. Okay, so it's a transfer of energy to reach thermal equilibrium. So aluminum gives water energy until they both have the same total energy, and thus they have reached the same temperature, so thermal equilibrium. The amount transferred from aluminum to water is going to be equal to each other, and that'll be the total amount of, or total thermal energy exchanged. So now, on your own, you are going to practice and review these concepts using the You Do. Check your work, and thank you for tuning in, guys.